Alt-R does work. All right, Monday, Lab 11. Let's get right into it. And let me plug this in advance so that I don't forget. And let's share screen. Shall we start with a PDF? Let's do that. Okay, let's go back. So we're not doing Lab 0 this week unless something drastic changes, which it probably won't, but who knows. So part 1 is to do with the differentiation. And depending on whether or not you have taken multivariable calculus, which is not a requirement for this class, I don't believe. Yeah, I think 1B was the last requirement, but basically what it is this. Where should I start by talking? So first of all, let's go over the actual code. Is this a partial differentiation part? Oh, no. The second part's a partial differentiation. This one's just regular differentiation. So ordinary calculus will carry us through this part. And if you're scared by the phrase partial differentiation, don't worry. We'll go through it. It's not as scary as it might sound. Okay. Helicopter speed. So let's annotate. Okay, well, you have a number line. It has like, you have like station 1, station 2, and like station 3. So I should call it landmarks 1 and 2 and 3. So there's like a helicopter. I'll just kind of draw a fish with like a propeller on top. And then it'll use sonar or whatever to have a car, give it little windows, and it'll pass like 1, 2, and 3. So it's going to measure the time it takes to pass by each of those coordinates. So let's say like we have x equals 1, 2, and 3. And then time it takes for it to pass 1, 2, and 3 is like time 1, time 2, and time 3. I'm seeing something in the chat right now. Never mind. Okay. Time 1, time 2, time 3. And what we're going to want to find is the speed, or an estimate of the speed. It's not going to be exact because we don't have information at every single point. But we'll find an estimate of x dot, also known as dx dt, at each of those points. So that and that. d over dt of dx over dt. So this is speed, velocity more precisely, and acceleration. It's 1D, so there's no really difference between speed and acceleration. I mean, you're only moving in one direction. Yeah. Oh, one more thing that we should be careful of. X and T are given in feet and seconds. So if it's FPS, if the output units are FPS, we're good. If it's MPH, then we're going to need to convert to miles per hour. So that's just a little conversion we'll need to do inside our code. And have I missed any other things inside the details? Devil's always in the details. Okay, this part we'll go over as well once we get to the code. Let me erase this part. Yeah, so this will have to kind of deal with the stuff that they kind of went over in lecture, a central difference method. Let me just illustrate what this means. Eraser, draw. Okay, I'm going to redraw the number line. 1, 2, 3. Let's say I want to find the speed at time, the speed after it as it passes first landmark. So the way we're going to do that is, well, but no, let's do this first. I'm going to do station 2, landmark number 2. How are we going to do that? Well, we know x1 and x1 and t1, and then x3, t3. We're going to use something called the central difference method. And what this is we're going to take, so velocity, speed has units of distance over time. So we're going to do this. x3 minus x1 over time 3 minus time 1. So like we're going to take, we're trying to find information at landmark 2. So what we want to do is take the difference between 3 and 1. So let's say if we're to graph this out, right? Here's time, here's x. Here's 1, here's 3. If we draw a line connecting 1 and 3, that's the slope of that line is what we're going to use as the approximation at landmark number 2. Now, here's the thing so the reason I want to do x2 first is to illustrate a problem with using the central difference method at, say, landmark 1. That's the first landmark. Now, if we were going to try and do the same thing, we need to do like x2 minus x0, but there's no x0. So what we're going to do instead is this. Instead of doing time 2 minus like time 0 or whatever, we're going to need to change this to the next best thing, which is 1 and 1. Because that's the first landmark. We can't really go any further than that. And similarly, with with a landmark 3, we're going to use so first of all, this is called the forward difference method. I should really illustrate these. So central difference method, CEN. I'll abbreviate this as forward difference method. And that's a bad F. There we go. Draw. Forward difference method. And you can probably guess this is x3 minus x2 over time 3 minus time 2. And obviously, we'll need to appropriate this for, say, an unspecified number of points. Although probably it's the size of x and t. Those will each of this will probably be its own separate part of the code. Central difference method, forward difference method, backward difference method. Okay, that's the first part. Now let's see if I missed anything. I think that's all we got. I don't think we're going to do the alternative second derivative formula. That's like you take the derivative of a derivative of position, which is a little bit more complexity than we're really satisfied with. Okay, by the way, to get acceleration from this, we just we replace, for example, let's just do one for example. To get acceleration, we're just going to do, let's see here, x2 ... is equal to, instead of x3 minus x1, we're going to do x dot 3. That is dx over dt at x equals 3. And then we'll just do t3 minus t1. So just replace that with the derivative, and then we'll be good to go. So you can probably guess we'll be doing speed first. Yeah, someone's asking third derivative. Yeah, there's, I'm not sure if we ever use the third derivative of the third time derivative of position. It goes velocity, acceleration, and I think the third derivative is something called jerk. I don't, we never use it. Yeah, jerk. Yeah.
I've never used it. I've heard the term too, but I'm also not familiar with any practical uses of it.
Sorry, what'd you say?
I also heard the term jerk, but I'm not familiar with any uses of it.
Life pro tip: don't be a x triple dot. Yeah, I've seen a shirt like that. Let's see. All right, well, let's see if there's anything on the next page. Okay, that's 1.2. Before we get to partial differentiation nonsense, let's go to the. I'm gonna stop sharing in 3, 2, 1, and let's go over to MATLAB. Let's see, which one was this? Speed FD, I believe. Speed FD. All right, here we go. Skeleton code for the first one. Now I said I showed a solution to this, so let's do that. Okay. This is what the solutions had. What string comp I is, it's just case insensitive. So this can be like a capital MPH or not capital MPH. I'm not sure. You'll probably be fine if they have like string comparison without the case insensitive. But oh, wait, let me check. I want to make sure that that's not actually. Yeah, these don't specify that it should be case insensitive in the PDF, so you shouldn't be penalized if you use string comp. But
however, I would rather recommend using the case insensitive version of that function rather than the case sensitive, unless the case like for this kind of text input for a function, unless the uppercase means something different, it is usually your code will be more robust by using this function. And by more robust, I mean it is easier to use by the user. It is harder that the user will accidentally break up your function.
All right, thanks, Jose. Pop quiz. How many feet are in a mile? Does anyone know this little factoid, or can use Google?
5280.
5280. Yeah, we'll want to divide that because it's like you multiply it by 1 mile over 5280 feet. So then this one, 60 times 60. Do. How many seconds are in an hour?
3,600.
3,600.
Well, I heard two
At
people
least
talking.
2.
Wait, I can hear.
3,600.
300, yeah. 3,600 or 3,600, depending on. Okay. This is what we're going to call last index. So, okay, the way they did this is they kind of compressed this whole central difference method into one single line. So instead of doing like, remember we had like x3 minus x1. I'm going to abuse notation here, but kind of just to illustrate the point. Instead of doing this, they kind of did this, like x, like let's say it's like x, they did like x end, no, 3 to end minus x. So they like subtracted 2 from, because x, it's like x3 minus x1, right? And then 1 is 2 less than 3. So they did x1 all the way until end minus 2. And then like they had that as the numerator. So like that's the way you would like compress all of that into, you can like do a for loop if you wanted, but like this is how you would do it with just a single line. So if I'm doing this right, x3 to the end minus x1 colon n minus 2. By the way, this whole thing's going to turn into a vector. So because it's a vector, let's see. Okay, so time, and this is going to be the exact same thing, 3 colon 3 to the end minus, what's this? Subtract 1. 3 minus 2 is 1. End minus 2 is just, well, n minus 2. Okay. All right, I have made a mistake in this line over here. Can someone tell me what it is? Remember that this is a vector and this is a vector. Yeah. So I see it in the chat. We're going to need a dot well, element-wise division. Every single one of those elements inside that, well, we're creating a difference vector. So difference of x, it's basically delta x over delta t. And we're assembling a vector of delta x's over delta t's. So I'll write delta x divided by delta t. Well, I guess this is the same thing for all of these, huh? All right. This over here, I'll just do it. It's x. What is it? X2. What do we say? Minus x. We can't do 0, so we have to do 1. And we'll do the same ones on the bottom. Here, I'll move this over.
Mixing T in line 12.
Line 12, what are you saying?
T.
Yes, I am. Thank you very much. Yeah, 2 mistakes, I guess. There we go. X3 and X1. Everything. Yeah. Okay, let me know if you see anything else. Okay, let's do forward difference. This is going to be central difference. And this is backward difference. Okay. Last but not least, backwards difference for the last index. Let's just use the x end and end minus 1 and end minus 1. Okay, does that look good so far? Okay. Okay, 6 x's. Okay. Looks good to me. All right, acceleration calculations. What I'm going to do is this. Copy that. Wait, what? Okay, copy this. So like we said before, instead of doing x, we're going to do, we store it in a speed vector. So we're going to place this as speed, ciao, and do the same thing for all of these. And the third line. So that's it. That's going to be it for the first part of problem 1. Okay, let me reference the solutions to make sure that I got everything. That was, yeah, replace everything with speed. End. Yeah, they use last index instead of end for the this speed last index and acceleration last index. I'm not clear. It's not clear to me why they decided to do that. I'm sure there's a reason. I'm pretty sure end works here, like instead of last index. So I guess because we're here, it makes sense because they're trying to, because they're creating a vector speed and acceleration. So okay, here, who can tell me? Okay, let me quiz you guys. What would happen if we changed this to end? What would happen? What would end be if we tried to run this line? Why can this index right here not be end? I also noticed someone saying, yeah, 2.2 would be helpful. Let me try 2.2 in the meantime. I want to see what that is. I remember it was pretty straightforward. Read trapezoidal. I'm not sure. Let's see. I think trapezoidal, Simpson, and Riemann are given somewhere in the lecture slides. I'm not sure, but sure, I can give you maybe part of that code then, if that's helpful. Maybe just like the trapezoidal, Simpson, Riemann part of that of 2.2. Okay, well, we can do that if we have time. Let's go back to MATLAB. What I was saying is this. So the reason why this has to be last index, right? So last index is like, let's say we have X number of, let's say like X equals 3, say. We have speed 1 equals this. It creates a vector called speed. Speed equals, I don't know, let's say 5. Now, if we're going to do this, it's going to increase the size of speed. So 5 ... until like last index minus 1. If we did end minus 1, right? When we say end, I'll change this to end for argumentation purposes. This end looks at speed and it takes the index of the final value. So in this case, it's going to be 1. So if we did this, this would be speed 2:0, which is going to be, I'm pretty sure it's going to be an error. You're assigning a value to an empty vector. So this is why we created this last index variable over here. So that we know that, I mean, another way we could do it is we could do end. If we did end, we would need to pre-allocate speed. Let's say we do speed equals zeros 1 comma last index, or just 1 comma num L X. We could do that, and then just have these be end. Now, part of the discussion is, so this can be end. However, because we already know what X is, we already have like a size of that. We're not like tacking on like 1 and then 2:n might change this to last index before I forget. Okay, but yeah, this is the final version. I don't think I'm going to touch this anymore. I think we're good for there. Okay. Where was I? I'll clear this. All right. Any question before we move on to 1.2? It's going twice. My gradients. Okay, partials. Oh, let's go back to the PDF, by the way. There we go. And we're going to do partial. Nope, too far. 2D numerical differentiation and gradient. All right. So a quick introduction to partial differentiation. F of x, y equals x, y. So let's just follow along with what they're doing here. So the partial is like ordinary differentiation, but it's like you have multiple different variables. So how do you know which to differentiate with respect to? So if we say this, partial f with respect to x, this means you treat x as a variable and everything else as a constant. So y is a constant. Treat y as like a number 2 or a number 3. So we would say that is, okay, derivative of x times a constant, that's just the constant. Now, if we did the other way, differentiation with respect to y, well, now we treat x as a constant. X is some number. X is 2y. So we get rid of that y because of the power rule, and we say x. So that's the partial derivative. Now, the other thing is what's called a gradient. So a gradient is just a vector that stores the partial derivatives with respect to, well, it's going to specify here, x and y. And what the gradient kind of represents, is the direction of, let's see, in this case, it's going to be, I always get this mixed up. It's either the greatest increase or the greatest decrease. So like, let's say our function is this, like here's like a box, and then we're going to graph like a two-dimensional, like a hill almost. Like I'm going to draw like kind of like a spider web, something. This is the top of the hill. And let's say we take a point right over here. So if our if it's saying that, I believe it's greatest increase. Yeah. So what this will tell you is it'll, at any given point x, y, it's going to compute the partial derivatives, and it's going to tell you which way it's increasing. It's kind of like if we did the 2D case. Like here's some function, and then we did like d, y, d, x. So if this is positive, then that means that you want to go like this way to get the greatest increase. And if it's dy over dx is less than 0, you want to go the other way. So like that would be like if it's a negative slope. Okay, well, let's not get too into the weeds of this, by the way. Let's just understand what we need for this problem. All right. Grad function above area. Okay, yeah. If we're given like x, y, let's see. Okay. You can kind of see how like it depends on what kind of function we're given. This can be really ugly or really simple. But let's just get into what we're actually trying to do. How many labs are there in total? Yeah, there's 12. 12 is the professor said there was lab 12 is optional, but it's not really optional, because if you don't do lab 12, you get rid of your ability to drop your lowest lab score, because like they submit 10 labs, and we're doing like 11 labs in total, including lab 12, because we skipped lab 7. So I would do lab 12 if I were you. That's the week of Thanksgiving, but you'll have until December 3rd to do it. Okay. Next page, I guess. Let's see what we're doing. Let me clear this in 3, 2, 1. Okay, we're given some function. We don't know what the function handle is, but okay, let's see. Function handle, we're given b box. So we're given some grid. Let's say we have like this is like from -3 to 3, -3 to 3. This is, by the way, is like your y. This is your x. I'm like kind of looking at the xy plane from like a bird's eye, not a bird's eye view, but like a diagonally downward view. And then at every single point, we're gonna like graph. This is gonna be like a surface plot. Like let's say like kind of like that. It's a hill, like a spider web. Hard to do with like a wireframe thing in 2D, but you get the point. So function handle, this is your f. This is the way you're going to plot kind of imagine a surface plot of x min, x max. That's these bounds over here. Total grid points. So that's going to be, let's say you have 10. Well, let's make it easy. Let's make it nice. Let's say it's 7. Let's say this is 7 and this is 7. So that's your n. And then the gradient is going to be, let's see, n minus 2. So this is going to be similar to the previous part, but kind of with partial derivatives instead of ordinary derivatives. So, okay, this one's a little bit more complex. So like, let's see what we're trying to do here. So note that your gradient's going to be n minus 2 by n minus 2 times, okay, times 2, because you're going to have y's in it. Oh, wait, hold on. Wait, Jose, are you here? Let's see. Is he here or is he? Yeah, Jose.
Yeah.
I want to ask you: is this? This is a three-dimensional array, isn't it?
And by yes, that is
Oh
a
dear, yeah. Okay. Okay. It is a okay. So what that's going to be is like it's kind of like you're going to make two arrays of size n minus 2. And n minus 2 is kind of like, if you kind of recall the central difference method kind of we did for the first part, you're going to like kind of compress like, oh, you took x3 and x1 to find information at x2. And then you're going to do a similar thing with like the partial difference. Yeah, maybe this will make more sense once we actually get into the code. But and then you'll do one for x and you'll do one for y. Partials of x, partials of y. So
So
Basically,
it's
that's
three-dimensional array with like you've got two n by 2 then n by 2 arrays. So one's for the x and one's for the y.
exactly. So for each point on the XY grid, your output, your gradient is a vector in itself. So for each XY pair, you get an XY pair. So that's why you need 2 elements per point on your output.
okay. Well, I'm gonna stop sharing in 3, 2, 1. Okay. Let's go to my gradient and see what we're gonna do. Okay. Let me reference my notes. Okay, so first of all, let's set up our points. We need to do a lid space for each of these. So we know the bounds. That's going to be, so as a reminder, I'm gonna do it partially for you guys, partially for me. B box is x min, x max, y min, y max. So the ones we're interested in for x, they're going to be, so B box is a vector, so we'll do B box 1 for the minimum, B box 2 for the max, and it's going to be the same number of points in each direction, so we're just going to do n for that. What about this one? Well, by process of elimination, comma n. Semicolons for purposes. Okay, partial derivative arrays. We're going to need, is this just initializing? Okay, yeah, they're just initializing. Okay. Should we do this part first? Here, let's just show you guys how they did it, and we'll kind of think through how getting that. It's going to be zeros, n, and minus 2. So we're going to get. Now, let's explain why they're doing this after we kind of get into the for loop. Is that right? Yes. Okay. We're going to loop over the number of elements in data for the partial x derivatives. And then we're going to do j equals, no, wait, there we are. My mistake. 2 minus 1. Let's see. Yeah, so if x data looks like, if we're doing, say, 1, 2, 3, 4, then j over here is just going to be from 2 to 3. Because what they're getting is, hey, let's look at x2 and use the central difference method to get, use 3 minus 1 to get 2. We're kind of compressing this information into like inwards towards the center. Okay, what else? It should be the same thing as what we did earlier. Why do that? Oh dear. Okay, we're given some function, and they're asking us to do f x data j plus 1. So we'll do, it's going to be, I assume, j plus 1. Yeah, okay, j plus 1 minus j minus 1. Wait, f. Oh, I see. Let me get this out of the way. So remember the previous problem, we had a function of 1 variable. Now we have a function of 2 variables. And that's going to be f of x at j plus 1, y at j plus 1. Oh, come on. Never mind. It's different. Okay, that's the first point. And then let's see, fx data. Plus 1 minus. That's the second point. And then we're going to set up, let me make this bigger. X at j plus 1 minus x at j minus 1. Okay, before we go on, let's try and let's kind of understand what's going on here. This part's unchanged from the previous problem. We're at j, and we might need to. Now let's be smart about this.
Here the indexes are tricky, so we should probably try drawing the grid at least rudimentarily to keep track where we are with I and j.
Sure. Does this look good, Jose? J. Let's just do this symbolically.
I do need 2 for loops. Don't you just need 1 to iterate over x on the center difference of x each time?
Mm-hmm. So use just the x for loop and just get rid of the j?
No, I just don't understand why you need the I for loop. Because I mean, if you just if all you want are the partial x derivatives, then you can calculate that. You only need to go through it once. You don't need to do it twice, I think.
So the thing is that we are calculating the gradient over a whole grid. So
okay. Yeah, never mind.
Yeah.
Okay,
so basically we choose one value of x and we keep it constant and we calculate the gradient over the various y's and then move to the next value of x and do the same. So we're calculating the grid like line by line.
Jose, why are they doing?
Wouldn't that be calculating the y derivatives though? If you're doing a.
Sorry.
Wouldn't that be the y derivatives? Because what you're doing is you're iterating over every single x. You're iterating over every single point in the x data, but your for the derivative portion you're using 2 to -1. Sorry, 2 to number of elements minus 1.
Okay, so it'll be probably easier if I draw these to answer your question. So just give me a second because I need to fix up my screen. Just one moment. Why are you doing this? Just 1 second. Okay. I can only draw on one of my screens, so that's why I have to do this. So basically, we have in the XY plane, like I am looking at it in plan view, like from above, and we told our gradient function to calculate the gradients within a box that that goes from x min to x max and y max down to y min. All right. So, and we want on each side, sorry, that's a very lousy drawing. I'm trying to do this on my laptop. So on each side of this space, we want endpoints. So something like this. And same on the other direction. They have the same number, 5, 6. And same for the middle, something like this, and you get the idea for the rest of the plane. So what we are doing on the outer loop is we pick some value of, is it x or y? Partial I comma j minus 1. So we will be varying over. Oh, okay. So on the first loop, what we will be doing is picking some value of x. So the first value of x, which will be our x min. So this guy over here, and we will be iterating over the different y's. So let me change colors here. So we will calculate the partial of f respect to x here. Then we will go to we will keep the x the same. We'll go to the next y, and we will calculate partial respect to x here. Go to the next one. Same idea. Partial of f with respect to
Sorry,
x.
I think I figured out what was confusing me. It's because I know that x data, the number of elements in x data and y data is the same, but I think it's like, for clarity, like for I, one through number of elements is actually y data. Like even though the numbers will be the same because they both have n values.
Sorry, I'm not.
Like so when you
I'm
calculate
following.
partial x derivatives, the outer for loop for
Mhm.
I is equal to 1 number of 1 to the number of elements of x data.
Mhm.
I think that should be number of elements of y data. Like technically it's the same because the number of elements in x data is the same as the number of elements in y data. But I think it makes more sense to say, okay, you're iterating sideways, so that's over y.
Oh,
Yeah, that's what sort of confused me.
In any case, I would do that here. I would change. You're probably right. We can probably change these to y data, and it would probably make more sense. But the outer loop, this one keeps the x the same, and we iterate this way. Then we go to I equals 2. So we pick this x, and we go back to j equals 2 through n minus 1. So actually, this one we don't calculate. So here we will be calculating this all the way through here in this direction. I equals 3. So this guy all the way through here. And so on and so forth. So we would be going this way, this way, this way. So that's what we are doing in. So this direction is the I loop. This direction is the J loop.
Okay, yeah. I was just confused because you looped over x data twice, and I was wondering like how that worked. But okay, that makes sense.
Yeah, you're right. Just for consistency, I would change that to y data. In this case, we could be a little bit sloppy on this, making use of the fact that both y data and x data have the same number of elements. So we could probably change both of these to an expression of n. Actually, n, the number n. But yeah, that's the idea of the true for loops.
We're changing this to x data as well.
Yeah, we could probably change all of those to n, but yeah, I think this way it's more clear. Thanks for the recommendation.
This is breaking my brain.
Yeah, the indexes in this one are pretty messy.
Well, let me just complete this line, and then we can come back to this if we have time. I need a break from this problem. Oh boy. Let's see what's different about this one. So instead, okay, x data. Let me just retranscribe it. Okay. Oops. Give me about 15 seconds to kind of do this. So f evaluated at x data j, comma y data. Also, Jose, why are we doing end +1 minus I and stuff like that?
Which one? N plus.
You see where we're doing
Yeah, like the n minus I plus 2, that kind of thing.
Mhm.
Honestly, I have not been able to figure it out. It seems like they go backwards, basically. Like they start with the last j value and they go back to the first one. I have not figured out why can't we do the opposite and just go on an ascending j value.
Yeah. Oh, whoops! I made a mistake. Yeah. Y'all can try it out with like going the opposite direction. I'm not sure why they decided to start at the end and then work their way backwards. But
I'm sure there's a reason. I'm sure there's a reason. Nobody would no human being would decide, yeah, I will count this very, very odd way just because they can. But honestly, I have not been able to figure out why.
yeah, why are they doing it here? Oh, why did my screen just shrink? Sorry, I minimized it, so I was looking at the not minimized, but like I kind of shifted it to the other side of the screen so that I could look at the solutions at the same time. Okay, that should be it for this one. I could think about this more, but I'm not sure how much good it'll do. Yeah, here's my gradient. Enjoy. Okay, is my screen like unshrunk or is there something else going on? Aiden. Okay. See, I may do that one or more times if I need to cross-reference something else in the meantime. Okay, that was, so once again, here's 1.1. I'll leave this up for 10 seconds. All right, my gradient. Leave this up for 10 seconds before going on to the next one. All right, Gauss integral. Fairly straightforward, define the interval, the step size, the function to be integrated and compute the integral in the end. And this will use, like, I think the integral function in MATLAB. I believe that's built in. Let me check that real quick. Oh no, you don't even need to use integral. You just f of integral. Yeah, because you're approximating it. Yeah, you'll just take like a sum. But in the interest of not giving you more than half of the answers, I'll leave it at that. Sum of ... Yeah. Okay. Now that's 2.1. 2.2 is this. And
Can
I
I back to
can
my gradient real quick?
my gradient, sure.
Yeah.
Any
thanks.
question or like just
No, I think I get it. I have to think through it as I'm like typing this out. It still seems like a bit dicey to me, but I'll have to like draw it out myself, and I think that would make more sense.
me too. If you can
Like
explain to
I feel like I can get it. It's just that like it's like a lot to like hold in my head at once. But yeah.
Yeah, if anyone wants to like think about this and like come back on Wednesday and like explain it to me and the rest of the class, like feel free to, because I want to understand why this is the way it is. Or if there's a simpler way, like if this works with like instead of end plus 1 minus I, it works with like how does this work? You're scanning from, yeah, if this works with just I, then yeah, go right ahead if it satisfies the test cases. So
yeah, it's one of those things where I think I understand it, but the devil's in the details, like the little things like the indices that would like cause your code to break or do funny things.
yeah, if you're
it's definitely one of those cases where probably if we just use the I in ascending order, because here we're going to the end and then going backwards, probably the other way, there's some weird case where function breaks up.
I mean, it might just come down to convention ultimately. Like, if I think what they're doing is this, they're making it like an XY grid, right? Here's the origin, here's Y, here's X, and then they're like starting up here, and then they're like scanning like from top left to bottom right, that kind of thing. Maybe that's what they're doing. And
that's what I think they're doing. I just don't know why.
Yeah. Okay. Makes sense. I think I understand why they're doing it now. Oh no, I understand what they're doing. I don't understand why they're doing it, but I understand what they're doing. Permission to move on for this problem? Yeah.
Oh yeah. Go ahead. No, I got it.
Okay. I keep wanting to call you.
I'll just like.
Yeah. Sorry. Go ahead.
No, I'll just go back and code it up, and yeah,
All right.
I'll come on Wednesday and like see if I got it.
Okay. Cool.
Perfect.
Let's go to, what are we? A Gauss integral? No, Roux sheet length. Yeah, a similar thing. Haven't looked too much into this, but I can here. Let's now let's just get this out of the way now. I'm gonna give you guys the trapezoidal, Simpson, and Riemann. So, where is it? Not this one. The next one. Okay. Trapezoidal rule is here's what each of those looks like. So you have the I'll write trapezoidal, TRAP. You have this one, and then you're taking the integral using the trapezoidal rule is this. You're taking the average of f at, I'll write x2, f at x1, and you're So first of all, find the average, f of x2 plus f of x1 over 2. That's the average. And then all of that multiplied by the step size. That's going to be this delta x over here. See something in the chat. Okay, Caden, why we have to include my Lagrange for lab 10 in our zip file? Haha, we're going to use Lagrange in the final part. So hopefully you did that correctly, / have access to my playlist from last week. Let's see here. Yeah, that's the trapezoidal rule. Simpson's rule, that's going to be, okay, do I have enough space for this? Close this, close this. I'll do it down here, I guess. I'm moving some stuff around in like the foreground, so in case it looks like I'm not doing anything. Found it. Okay, Simpson's rule is, yeah, Simpson's rule a little bit more complex, but here it is. You'll need 3 points. If I'm looking at this right. You'll have, it's like delta x over 3. Actually, no, you know what? I think I'll just give you the code. You can like look these up on your own. I'm gonna, let's see. Jose, do you know if it's in the lecture slides?
I think it is, but I'm not sure actually.
Could you check which slide that's on?
Yeah.
I'm sure.
I'll look for it.
I'm sure there's a slide that has like all of the different rules on it, but let me just present it in code. And then if you guys want to look at the actual ones, then they're on there.
Yeah, I'll look for the respective slide.
And wait, which Riemann are they doing? They're doing, that's a left one, I believe. Okay. So without further ado, let's do it. My screen should shrink again. That's because I'm cross-referencing. Okay, we'll do the sum of, so first of all, we'll take the average. We'll do f of x. We'll do like the compression thing we did before. So we'll do f of x, and then x is going to be the, well, it's going to be a string of x values. 1, 2, not end, but n minus 1. That's going to be, so everything up to the second to last one. And then we're going to add that to x of 2 to end, well, just end. And we'll take f of x of that. Before we do the sum, we're going to do, here, let's get rid of the sum for now so we have to deal with one less parenthesis. All of this divided by 2. We're going to take that, we're going to multiply that by the step size, which we'll define earlier. This needs an underscore. All of that, take the sum of that. That's the trapezoidal rule. Now, okay, let's see here. It's like, because 1, 4, 4, 2, I believe. So no, we'll do the sum last. So step size divided by 3. No, step size times 1/3 times the sum of f of x 1 colon 2 comma end minus 2. So on the number line that looks, so 1, 2, 3, 4, 5. We'll do these ones. Hold on. 1 colon end minus. Oh no, n minus 2. My bad. So it's every other one inside this span over here. So 1 to 3. So that'll be like, let's say we'll do 1 and 3. And the next one we're going to do is 4 times f of x at 2, every other one, and minus 1. Then we'll just tack on another one of these. It's the average of 3 points. Let me make sure I have all of these parentheses correct. Okay.
So I found the actual slide. If you wanna take a look at it, it's not really necessary to code this, but I mean, I find that Simpson's rule, it's not the most intuitive integration, numerical integration scheme that there is. I'm not saying that it's wrong in any way, of course not. It's just hard to understand. But if you want, I can share my screen for a second.
Let me finish typing this out and I can share it with you.
Okay.
And some of that. Does that make sense? Yeah, some of. Yeah, you can do the step size inside or outside the sum. Let me expand this out, and then I'll leave this for 10 seconds until. Here, let me clear this. I'll leave this up for 10 seconds and then I'll turn it over to Jose to explain stuff. Okay, that's first parentheses is for the sum. Wait a minute. Make sure we have the right number of parentheses. Oh no, we need that last one. That's for the sum. That's for the. Yeah. Okay. Stop sharing 3, 2, 1.
Okay, I'll start sharing. Wait a second, I lost my pen here. Let me maximize this, and I'm gonna share this screen. Okay, so the idea that's going on behind Simpson's rule is that if we have some function p, wait, I don't want to do that. I want to annotate. Where's here? So if we have some function p, shown here in red for as an example. Oh no, actually, let me correct that. If we have some function that we want to integrate, like this function f that we have here with some random shape, the idea behind Simpson's rule is that it can be approximated as the area below a parabola, which is the red function shown here. And for the area between under a parabola like this, we can calculate it by calculating f of x 0, f of x 1, and f of x3, and we can assign some weight to each of those. What's that?
Is that x2, f of x2?
Oh yes, sorry, f of x2. And we can assign some weight to each of these, and like we will assign approximately 4 times more weight to the central point than to the 2 outer points, and we multiply that by a third of the total distance between them, which is this formula that you have down here. And basically you're approximating the whole parabola, the whole function by many different parabolas. You have an example here where you have this parabola to approximate the area under the function, and this other parabola to approximate the area under that function under those different segments. And as with all numerical integration algorithms, these becomes more accurate the closer the points are, or the smaller the segments are where you are interpolating, because you can see in the, it's very noticeable on the parabola on the right here that that's not a very good approximation. We are losing all this area over here, and it kind of cancels out with some of this area that we're counting that we shouldn't, but not really. But if you made the size of the intervals smaller and these points were closer, you would probably have, let me try to replicate that portion of F in that area. You would probably have a segment that goes from here to here, where if you input a parabola, let me draw it in blue, to approximate it, it can do whatever outside this bound. Within my segment of, I think it's 2h, and actually this is also 2h, not h, as I said before. So within the span of that segment of 2h, this is a pretty good approximation of the area below the function. We do that for the next segment, something here and here, and we would probably have parabola, let me draw it in green, that goes like this. And again, that is a pretty good approximation of the area under the curve. And the whole idea behind using parabolas instead of just a Riemann sum, it's that for polynomials and basically curvy functions, it is more efficient to say, okay, let's make this whole area into a parabola that does something like this. Let's input another parabola here and another parabola here, and we have these three big segments. It is more efficient that doing that than doing a traditional Riemann that, okay, let's add this square, this square, this square, this square, because you need many squares to appropriately follow the curve function. So in this example, in these slides, the Simpson rule looks kind of silly, and why would we even want to do this? And yes, because the segments are really big, really coarse. But the whole idea is that probably to appropriately integrate this function, we probably need, I don't know, 100 parabolic segments within a tolerance, whereas we would need probably 10 or 100,000 Riemann points. So it's a lot more computationally efficient to do this on certain type of functions, on curvy functions. I also mentioned that all numerical integration algorithms, their accuracy grows as the meshing goes thinner. That is, there are a few exceptions to that rule. One of them is Gauss quadrature. So if you're not familiar, you could look for some YouTube videos on this. It's a numerical integration scheme developed by Gauss, the famous mathematician, and it's simply beautiful. It basically states that if you have a degree 5 polynomial that looks like this, it is sufficient to take, I think it was p plus 1 points. So it will be sufficient to take 6 points on very specific locations and add the values of the function evaluated at those points to calculate exactly the integral, which I find fascinating. It's not related to this lab, but it's something that has a lot of uses in engineering, and it is a beautiful topic. So if you have time and are curious about numerical integration algorithms, search for Gaussian quadrature. I'm gonna clear everything in 3, 2, 1. There we go. And I'll give the screen back to you, Dennis, so we can go over the code.
Thanks, Jose. Very informative. Here's since let me take over everything. So here was okay. So roof sheet length 2.2. We'll leave this up for maybe 5 more seconds. I won't show the entire thing just because. Let's see. Next one. Oh, I see some stuff in the chat. Gaussian quadrature. So trinomial integral. I don't think we need to just look in the PDF. You can do this in exactly 1 line. Now, once we do that, that's 3.1. 3.2 is this. We'll do a Simpson integral. And let's see here. Let's go to the PDF. Oh, I need to stop sharing actually. Okay, so this is gonna kind of build on 3.1, but I think we'll manage. Simpson's rule. So from A to B, we're gonna evaluate some function. We're not told what it is. It's just an input. Dx, we'll say. So it's gonna be some function, and then we're going to subdivide this interval from A to B into 2n equal parts. So n is going to be, let's say 10. So we'll have 20 of these rectangles. Imagine that's 20. So we're going to want to do 2 things. We're going to do the value of it, and then we're going to take the error of it. So this is why we need the function lab10, so the MyLagrange, and to include that. I'll stop sharing. 3, 2, 1. So if you haven't looked at 3.1 yet, it's basically you're computing the result of, you're integrating a parabola, a quadratic, if I remember correctly. Yeah. So now let's go to the code. Simpson integral. Shrink this just to make sure that we can see both that. Okay. So we're gonna want to start with a linspace to get. So we know our left bound and our right bound, that's A and B, and we'll subdivide it into, well, we want 2n rectangles. So we're going to need to do 2 times n plus 1. I don't think I need parentheses actually. So that's going to give us 2n, because that's the number of points we need to bound 2n of those rectangles. We'll initialize I as 0 because we're going to scan over all the rectangles, is the idea. And we're going to add that to I. So this is the structure that we've seen over and over and over again. Initialize and then loop. Initialize I, and then for I equals every other number between 1, so it's 1, 3, 5, 7, 9, all the way until the number of elements. So this is always going to be an odd number, first of all. So there's going to be an odd number of elements in X. So it'll be like 1, 3, 5, 7, 9, 21, let's say. So we're going to scan over all of those. Let's say like 1, 3, 5, ... And then like the last numbers are say 21, 23, and 25. So it's going to stop at 23. It's going to scan over here. Now, current polynomials. So Lagrange polynomial, once again, we're going to want to do, let's see. Okay. We have a bunch of, so as a reminder for lab 10, we're computing the Lagrange polynomial that interpolates x and y values. So we're going to do, here are your x values, here's your f of x values. Now our x values are going to be indexed from I to I plus 2. So we're going to start at 1. So this is going to be x from 1 to 3. And then f of x is going to be the same indices. So one more thing that we'll need to do for Lagrange, we're going to need to make these column vectors. And we're going to need to make this one match the same indices, I to I plus 2. And take, one more parenthesis and then take the transpose of that. Nope, we already have a semicolon. I'll expand this out once I'm done here. Okay, so for the next part, we're going to want to use the one from the previous, the 3.1 to, we're going to input A and B, which are our xi and our xi plus 2. So that's our left x and that's our right x. And current polynomials, that's going to, what is that output again? I actually don't remember. I think it's, yeah, it's just a bunch of coefficients, I believe. So then it'll take that and, so this will, let's see, Lagrange polynomial. You're given 3 points, so you'll get a quadratic. Yeah, that makes sense. So you'll get 3 coefficients in these. So A0, A1, A2. You're interpolating 3 points, you get order 2. Now, the true integral, this is the actual, the actual integral that, MATLAB has a built-in function integral. So this is what you're going to compare your I to. You're given, your I is just an approximation. So for this error, we're going to calculate I minus true. Okay, I've made a mistake here. What is that? What else do I need? I want my E to always be positive.
Oh, absolute value.
Yeah, absolute value. We want abs. Don't want to miss anything. Okay, let's stop share.
What's the input for Lagrange polynomial? I didn't understand that part.
Repeat that again.
Or the input for Lagrange polynomial, and also like, is that from?
That's from lab 10. So, okay.
Okay.
I think the solutions have an error. This should be my Lagrange. Is there a underscore? There is an underscore. There's always an underscore. All right, this should be my Lagrange. So Lagrange polynomial is just, it should be my Lagrange, whatever you use for lab 10.
Oh, so what's the input for this? I don't.
Okay, let's see. It's a bunch of x and y coordinates. So like, here's your x, here's your y. That's it. Those are your inputs. And then Lagrange is just going to like, oh, here's a point, here's a point, here's a point. And then you're going to interpolate between that. Using those x.
Oh, so you just create a lin space of 2n plus 1. And
yeah, so you'll have so be careful with like, so we're going to need to take 3 points out of this. Let's say this is like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. we want our current polynomials to be a quadratic, because trinomial integral only evaluates order 2. Otherwise, it doesn't work. So my Lagrange, so we're going to take out, let's say, 3 at a time. So 1, 2, 3. The next loop's going to take out 2, 3, 4. Next one, 3, 4, 5. And each of these is going to output. What's it going to output? That's going to output a current polynomials. So let's say like current poly. Am I answering your question so far?
Kind of. I'm not really sure. I guess I'm confused by the lab spec when it says like you must use the function in your own lab to get the coefficient of the Lagrange polynomial. So you get, so basically you're given so you're given a function, and then you compute the Lagrange polynomial of that function, and then you put that into the trinomial integral to integrate, and then you compare that to the actual. Is that the goal here? So it's like you convert the function into a Lagrange polynomial.
Yeah,
and then you integrate it, and then you compare that integral with the true integral of that function. That's what's going on. Okay,
you're
yeah,
kind of breaking. Yeah, you're breaking up the integral into like chunks that you can, like you're taking into like 3-point chunks. So this is like my Lagrange, like 3x points, 3y points. So that's you're doing it in. I'm not even sure if I can draw this out, but yeah, I mean, well, it sounds like you're.
Yeah, so basically you're doing more or less what we were discussing on when I was sharing my screen. You're breaking the function into segments, which you approximate with a parabola. Just that. Let me.
You can draw on this.
Okay, so let's say the actual function does something like this and goes down and up again. So we broke the function into these segments, and we take a group of 3 points, this, and this. So as Dennis was saying, we have the 3 values of x here, x1, x2, x3. We have 3 values of y corresponding to each of those, and we put in a Lagrange polynomial. That is, we approximate a parabola, because if you recall what a Lagrange polynomial does, and correct me if I'm wrong with this, Dennis, is that if you take a given number of points, let's say 3, it gives you out the lowest degree polynomial that can pass through all of them. So in this case, it will be a parabola, something like this. Like you can have higher degree polynomials that also cross all the same. Like you can have something that does this, but Lagrange gives you the simplest one, which is a parabola.
So the degree of the polynomial will be the degree of the polynomial will be 2n. If
it'll be 2.
I think generally it will be the number of points you give it minus 1. So for 3 points that are not in a perfect line, you need a parabola. For 2 points, you can do it with a line. And for 4 points, you probably need a cubic, so on and so forth. So in this case, we're dividing this into like chunking it into parabolas.
Right, but even though you divide into 2n pieces, you only take the first, second, and third points.
Sorry, can you repeat that?
Oh, I see. You're doing it. So you basically do the integral bit by bit. Okay, that makes sense.
Exactly, bit by bit. And then it showed down below the chunks. So for the red one, we would have approximately a parabola that goes like this, Oh well, like you got it there. Down and upward facing parabola for the orange one, and another downward facing for the last purple bit, which will not necessarily perfectly align with the function. Probably the function is not exactly a parabola between these points, but kind of. So it would be a good approximation for numerical integration.
Okay, yeah, that makes sense.
I
So,
tried learning to draw over the summer. It has not worked out.
So hopefully these diagrams help a little bit to understand what we're doing. And also on the why are we doing it, since MATLAB already has its own integral function. The answer is, well, there could be many answers, but the most common one is computational efficiency, because probably you're doing this, like dividing this whole complex function into 3 parabolas, it's a lot fast. It's probably a lot faster than just chunking it into a million points and whatever the integrated MATLAB function does. So if this is something you need to do, I don't know, several million times for any calculation you're doing, for any project or something, then this does matter a lot. It can change a problem from something that you can solve in an hour of computation to something that you need to leave a computer running for a couple of weeks. So this does matter on big projects.
Okay. Thank you, Jose, first of all. Is there anything that people want to go back to after we're done here? This is the last one we're going to talk about today. I know it's a longer lab. Uh, 2.2 one more time. Okay. Clear this in. I'll leave this up for 10 seconds, and then we'll go back to 2.2, roof sheet length. So, all right, let's go back to 2.2. I guess we don't really need to clear those drawings, huh? Okay, take screenshots.
Oh, sorry, I cleared them beforehand. Well, they'll be uploaded.
Oh,
if
people need, but I think I'm not sure how many people know this, but I think this will be useful. Win Shift S on Windows, and what is it? Command Shift or Shift Command 4 for Apple. Is that how you draw Apple? I'm actually not sure. I don't have an Apple. WinPrint screenshot. Wait, let me try that. I think like WinPrint screenshot sends it to like a screenshot folder. The difference with WinShift S is it copies it to your clipboard. So I'm not. If you prefer that, then that's what WinShift S does. So both of those work though. If you want to take a, so bottom line, that's how you take a screenshot if you're the professor is taking a showing a quiz question in class, or if you want to take a kind of a screenshot of this while it's on screen without having to wait for the recording. And the recording will be posted by midnight tonight. A lot sooner probably. It just takes a little bit of time for the video to compile and for me to upload. So yeah. And if you don't see it in the playlist, I mean, sometimes I accidentally upload and it just doesn't add to the playlist for some reason. So just like look on my YouTube channel, and then maybe it's like it shows up in the most recent videos. So sometimes that happens. And I try not to do that. Okay. Anything else? Or can I stop share and stop the recording? So I guess for recording purposes, I can just kind of speed through this, and then people can pause the video once they see the solution they want. So 1.1, 1.2, 2.1, 2.2, 3.1, last but not least, 3.2. Okay, I'm going to stop share. 3, 2, 1, and stop the recording. Alt R.